Okay, so the plan for today is we're just going to start with a little bit of admin just to outline what this course is about, particularly for those of you who are actually doing this for credit. And I know that's probably about half of the audience here. And there's a few people just auditing it or trying to learn something about reinforcement learning. So please, everyone feel very welcome. Then we're going to move on to really, the content of this whole class, which is reinforcement learning. I'm going to describe what it is, so you have a clearer idea of what reinforcement learning is really about. And to do that, I'm going to start by just introducing the problem, and then talk about, first of all, what the problem setting is. What do we mean when we want to solve a reinforcement learning problem? Where does this fit within machine learning, within science? What are we really talking about? Before we'll start talking about solution methods. Where we'll start to talk about what does it mean to actually build an agent which can solve the reinforcement learning problem. So that will be this section, inside an RL agent. And then finally we'll talk about some of the key problems within reinforcement learning and start to get some insight into the key components of what it actually means to try and solve this problem. Okay, so just to begin with, let's start with some admin. We're trying something new this year. So in previous years, this has been a 9:30 class. So today, okay, we're starting at 9:30. But for future classes, if we could try and start at 9:15, I know that because there are a number of people here, I'd actually like to encourage people to ask questions and make this a little bit interactive. And that means, typically I found that means we need just a little bit more time to get through the content. So it can be a little bit more relaxed and not something where we try and go right up to cramming everything in at the last minute. There is a website. This is the website on which all the teaching material for this part of the class will be posted, the reinforcement learning class. All the slides are up there. However, I should note that I reserve the right to change the slides right up to the last minute, and I often do. So if you print them out in advance and turn up with them, you might find they're slightly different to the ones I actually teach with. But I will update the website and make it clear when those slides have been updated after the class, so that if you're trying to revise for the exam at the end, you should know what the actual material is that I've taught with, and that is the examinable material for this year. It would be great if everyone could join this Google group. That will just help us to coordinate. This will also be the whole of advanced topics with Arthur Gretton as well. We're going to coordinate on this mailing group, so if there are cancellations or issues that come up, or issues regarding the assignments in particular, they can be communicated on this group. So it's just handy for us if there's one place where we can get in touch with everyone. And feel free to email me if any issues come up during the course of this class. Okay. So for those of you who are taking this course for credit, I think Arthur explained this in the first class, but very briefly, again, this is a split class between the advanced topics, covers both the kernel methods component and the reinforcement learning part of the course. We teach them as if they're two different courses. So you can think of them as like two half courses that happen to sit under the same umbrella of what we call the advanced topics class. What that means is that we arrange it so that you don't have to take one, or you can get away with just taking one or the other. You don't have to sit in both parts of the class. And so the way we do that is there's an assessment for the RL part and an exam for the RL part. There's an assessment for the kernel methods. And in the exam, you can choose kind of which or both of those questions to answer. So specifically, the RL part will be 50% coursework. The whole overall assessment will be 50% coursework, 50% exam. And there'll be two different assignments. You can choose one or the other. If you happen to do both of them, the bonus you get is that your overall score will be the max of how you did in both of those assignments. So it can be a significant advantage for those of you who do both of these assignments, but you can also get away with just doing one of them. And in the exam, the way that we get around this issue of having two half classes is that there are 3 reinforcement learning questions in the exam and 3 kernel methods questions in the exam, and you can choose any 3 to answer in the exam. So if you do study for both parts, you have the flexibility of choosing amongst them, but you can again get away with just learning one part or the other, although you're really just stuck with the course, with the questions that I will offer you if you're doing the RL side, or Arthur if you just do the kernel method side. Okay, is that clear to everyone? Good. Okay, so textbooks. So the main textbook which we'll sort of be semi-following on this course is called An Introduction to Reinforcement Learning by Rich Sutton and Andy Bartow. So this book is considered the seminal textbook for reinforcement learning. It's actually available free online. And in fact, Rich Sutton is currently working on a second edition to the book, which is also available online in its current draft. And we'll be using actually the notation from the second edition in this class if you just want to be compatible and understand exactly by comparing between them. That's probably the one to look at. So this is a really good choice. However, some people prefer something a bit more concise. This one is maybe 400 pages and very readable, but it's also, gives you a good overview and sense of the big ideas of reinforcement learning at a sort of intuitive level. However, some people prefer a more rigorous sort of mathematical textbook, and so the one which I'd recommend if you're one of those type of people is by Csaba Szepesváry. It's called Algorithms for Reinforcement Learning. This is a much shorter textbook. It's less than 100 pages, covers all the main ideas very concisely, much more sort of terse style. But you'll get less of the intuition, but more of the rigor, and you'll really get sort of, for those of you who prefer the theoretical side, I find that this is what some people actually prefer reading. But the style of this course will be somewhat closer to the first textbook. Okay. So let's start by trying to understand reinforcement learning and get some idea of, what is this thing we're all sitting here to try and learn about and talk about. So to begin with, let's try and sort of place it within the whole field of science. And I think one of the special things about reinforcement learning is that it sort of sits at the intersection of many different fields of science. So we have here in the middle of this sort of Venn diagram, we've got reinforcement learning, and what this is supposed to illustrate is the fact that for many of these different fields of endeavour, there is a branch of that field which actually is trying to study the same problem that we're going to talk about in reinforcement learning. So what is that problem? It's essentially the science of decision making. I think that's what makes it so general and so interesting across many, many different fields. It's a fundamental science. It's trying to understand the optimal way to make decisions. And so this comes up again and again. So in computer science, we study this under the umbrella of machine learning, and specifically reinforcement learning, and that's what we'll look at in this course. But if you go to engineering and talk to people in the engineering world, they have a large part of engineering devoted to what's called optimal control, which essentially is studying the same type of problems with many of the same methods under different names, which is, in other words, how to optimally decide a sequence of actions so as to get the best results at the end of the day. In neuroscience, it turns out that one of the major discoveries in neuroscience in the last couple of decades is actually an understanding of how the human brain actually is believed to make decisions, and that a large part of the human brain is devoted to what's called the dopamine system. And this neurotransmitter dopamine actually exactly reflects one of the main algorithms which we'll study in this course. And so the reward system of the human brain is really studied widely and a major part of neuroscience now, and it's really people there are trying to understand exactly the reinforcement learning methods that we'll talk about in this course, and it's believed to underlie human decision making as well. Again, in psychology, there's been a lot of work going back to Skinner and so forth on classical conditioning and operant conditioning, which again is trying to understand how animals make decisions, how and why animal behavior occurs. If you give them some rewards and you see that this animal start to salivate, the theory that underlies that is essentially reinforcement learning again. In mathematics, there's again an equivalent to reinforcement learning, studying the maths of optimal control again, and it's known as operations research. And finally, in economics, there's the fields of game theory and utility theory and bounded rationality, and these are all, again, getting the same questions of how and why people make decisions if they're trying to optimize their utility. So really, it's something fundamental, and I think it's something of general interest in many different areas. So if we zoom in a bit to this diagram and try to understand, in this course we're going to talk about reinforcement learning. So there's a few things which differentiate reinforcement learning from supervised learning and from unsupervised learning as well. And so let's just see if we can understand those distinctions. So the first one is maybe the most obvious, that there's no supervisor. When we do reinforcement learning, no one tells us the right action to take. Instead, it's a trial and error paradigm. there's no supervisor. There's just this reward signal saying, that was good, or that was bad, or that was worth 3 points, or that was worth minus 10 points. No one actually says that was the best thing to do that action in this situation. So there's no supervisor. The second major distinction is that when you get that feedback saying good or bad, it doesn't come instantaneously. It may be delayed by many steps. So in the reinforcement learning paradigm, you make a decision now, and it may be many, many steps later that you actually see whether that was a good decision or a bad decision as the kind of the decisions that you may unfold over time, and it may be that it's only retrospectively that you realize that was a bad decision, because at the time it looked like it was very good, and maybe even you got positive rewards for several steps before some catastrophic large negative reward. So in RL, the feedback is delayed, and that makes it very different again. Furthermore, time really matters in RL. So we're talking about sequential processes, sequential decision-making processes, where one step after another, the agent gets to make decisions, pick actions, see how much reward the agent gets, and then optimize those rewards to get the best possible outcomes. So we're not talking about IID data here. We're not talking about the classical supervised or unsupervised learning settings, where you get some IID data set and you just get to learn on that data set. Here, we've got a dynamic system. There's an agent moving through a world. And imagine a robot sitting, walking through some environment. What that robot sees at 1 second is going to be very correlated to what it sees at the next second. This doesn't really, the IID paradigm that we're familiar with doesn't apply to RL. And specifically, perhaps the most important way in which IID breaks down is that in reinforcement learning, the agent gets to take actions. It gets to influence its environment. It gets to move around. Imagine this robot. It gets to move around in its robot. If I'm in the robot and I walk to this side of the room, I will receive very different data. So I'll see different things. I'll get different rewards to if I'd moved over to this side of the room. So the agent is actually influencing the data that it sees. This is like an active learning process. So it basically got this combined set of differences that defines the RL paradigm and makes it quite distinct. But in many ways, this is really the paradigm that's faced by all of those fields of science we just talked about when we try to understand what it really means to optimize a sequence of decisions. Okay, so let's try and make this concrete by talking about some examples of what would be our reinforcement learning problems. Let's not talk in the abstract. Let's get a feel of what RL is all about. So I'm just going to kind of illustrate this with a few examples, and then we'll have a couple of videos. This is the first lecture. It's nice to have a bit of fun. And so one example would be flying stunt maneuvers in a helicopter. We'll see a video in just a second. So here, that you've got a helicopter being controlled. You want this helicopter to make a particular maneuver. It's not that anyone tells you at any given moment, yes, you've done the right thing, or no, you've done the wrong thing. It's that at the end of some period of time, you want to have executed this maneuver, and maybe someone says good or bad at the end of it. And crashing is typically very bad. Another example would be to play the game of backgammon. And one of the famous successes of reinforcement learning is when Jerry Tassaro defeated the world human champion at the game of backgammon, just by reinforcement learning. So this is a system that was basically playing the game again and again, and just by trial and error learning, figured out a way to play backgammon better than humans. Another example would be to manage an investment portfolio, where now the time steps are decisions which are being made perhaps in real time. Perhaps there's some stream of data coming in this trading agent, and it has to make decisions about what to invest where and in what products, and the reward in this case might be money, and it's trying to maximize the amount that it makes over time. But it's a clear example of a reinforcement learning strategy, a reinforcement learning problem. Or to control a power station. A power station is an RL problem in the sense that there's a sequence of controls that you can make of that power station. Perhaps the controls are, it could be the torques on the motors of how things are being converted. It could be different ratios that are controlling the batteries and so forth. There's all kinds of different tweaks. In a wind turbine, you have the blade pitches and so forth. There's all kinds of different parameters which can be controlled at every second so as to optimize the throughput of this power station. So there are many different decisions that can be made there over time, and there's some long-term goal, which is efficient generation. Another example would be to make a humanoid robot walk. So you don't want this thing to fall over. You maybe want it to get to the other side of the room. How do you do that? This is a reinforcement learning problem. There's rewards at every step telling you whether it's falling over or whether it's making progress. and at every step it's got to learn for itself how to figure out this behavior of walking across the room. Finally, this is an example from DeepMind, where we've been working on this recently. How do you get a single program to play against a suite of different games? So you just sit down in front of an Atari emulator. You want to play this Atari game, say Better Than a Human. How do you do that if you just sit down, watch a stream of video coming in, and get to control the joystick? How do you learn how to play that game to some good level and get the maximum amount of score on that game? Okay, so let's have some videos just to make this a little bit concrete. So each of those examples I just gave, I should add as a real successes of reinforcement learning. So they weren't just abstract examples. They're things where reinforcement learning agents have been successfully built to solve each of these problems. So this is a nice example of the helicopter. So it's not a full-size helicopter. It's a fairly substantial model helicopter. So when it crashes, it doesn't cost like $1 million. But it's learned through reinforcement learning to perform particular stunt maneuvers, which are described down in the bottom right there. And it's being asked now to kind of show off and execute all of these behaviors that it's learned, essentially through trial and error. Basically, this thing learned by accumulating experience, learning from that experience, being told a reward function of what's good and what's bad, and then executing that behavior to see all of these different maneuvers now. Some of them are quite fun. And believe me, if you just take a model helicopter and try to control it yourself, it's very hard to make it fly upside down, or to do a split S, or to do some of these maneuvers. Okay.
What they train manually, what they simulate, the training from the simulation, or it was in real time, just refly?
So the way this was done, they built a model, they learned to model, so we'll come to this later in the course. They built a model first. Once they had a model of how the helicopter behaves, they then did some planning with respect to the model, and they were able to actually then, so the learning was done on the model offline, and then applied to so the model was learned from real data, and then it was able to learn with respect to that model how to perform optimally. Show one more movie. So this is an example of something we've been working on. This is the agent which plays the Atari games against. So this is basically a system which is learning by trial and error. It doesn't know anything about each of these games. These are all different Atari games, for those of you who are familiar with the classic Atari console. And all it's shown is basically this video we're seeing here, and it gets to control the joystick, and it's told how much score it gets. And it basically has to learn to figure out how to play the game with no knowledge. No one tells it the rules of the game or what's going to happen. It just figures out how to play very well and maximize its score through reinforcement learning. And you can see the games are very different. This is a side-scrolling game where you have to kind of blow up all of these things and accumulates score by shooting stuff and moving along. Some of them are sort of pseudo 3D, like this Battlezone is like a pseudo 3D game. We don't claim these are good games, by the way, just that we build a reinforcement learning agent to be able to play them all, and it learns to do better than humans in more than half of the games that we played against. This is a really ridiculous game where the game is literally to make a chicken cross the road, and it learns to do that. This is more of a classic kind of shoot 'em up Space Invaders type game called Demon Attack. Learns to kind of duck in and out of the bullets and shoot all the aliens. This one is Pong, the classic original Atari game, and we're controlling the green guy here and basically learning to hit it right. You have to get these like sharp angles off the corner to be able to get it past the opponent, and it sort of learns this strategy and eventually learns a perfect strategy of winning every game. Yes?
You're allowing, presumably, the reinforcement algorithm to respond to stimuli in a much shorter space of time than a human would be able to do that. Simply because of the hand-eye coordination, for example, there must be a lower...
Actually, no, we tried to match it to roughly human. So we make decisions at 15 hertz, which is not way beyond what humans are capable of. So
it's a fair...
I think it's reasonably fair, yeah. So this game is Sequest. Here you'll notice it has to do like delayed decision-making, like it has to go up to the top, fill up with fuel, which doesn't get any score, so that then it can go back and shoot agent, all these different monsters and things, and fish and sharks, and go back and get more score. Here it has to jump around this whole grid, turn everything yellow whilst avoiding this coily thing here. It can use this little teleport thing, and the goal has to figure out just from these raw joystick maneuvers how to kind of fill up the whole screen and get this big score at the end by doing that. And again, we haven't told it anything about these different games. It's just figured out what to do just by trial and error on the joystick. This game's kind of weird. It has to sort of sweep this thing around and get the liars whilst avoiding the things which will kill it. This one, I guess, I'm probably familiar with, Space Invaders. We've got this agent that's being controlled, and it learns this very human-like strategy. First of all, it captures the mothership. Also learns a very human-like strategy of doing things a column at a time, which gives it more time as the game speeds up. It takes longer for the aliens to move from one side of the screen to the other and move down, and that actually gives it more time to be able to sweep up and kill them all, and it figures out that strategy for itself. This game, boxing, again, a little bit of a strange Atari game. I don't think racial stereotypes are intended with this one, but anyway, so we're controlling this one on the left and learning this strategy of pummeling this other guy into the corner there. Right, so a real variety of different games there.
How long does it take to train this algorithm? And were there any ones that were particularly tricky to train?
So yes, it
just off a MacBook, for instance.
Yeah. So on a MacBook it would take quite a while. We use it on a GPU.
Yeah.
So using deep learning. So there's a whole story there of exactly what we do. But roughly speaking, it takes around 3 or 4 days of training to get to the human level of performance on each game per game. So 3 or 4 days of compute time to do that. Okay. So that hopefully gives a flavour of what RL's about. And I don't want you to think that RL is just about games, but actually a lot of my background in reinforcement learning has been on applying reinforcement learning to games, to board games, to video games, and I think they're kind of fun to talk about. So, some of the examples will be drawn from my experience, and so I really want you to see this as just examples of how RL can be applied, and in that sense games are just like little microcosms of real things which happen in the real world, which have very clearly defined rules and help us to understand how these ideas can be applied. So don't think it's just a game-specific idea, it's very generally applicable. Okay, so let's talk now about the reinforcement learning problem. So any questions first about, before we move on? I think we'll start to get into more details and understand things a bit more clearly in just a second. Yeah?
Just on the Atari games thing, do you use what it learns on one game and then sort of transfer that knowledge to a different game, or is it starting fresh each time?
It starts fresh each time.
Right.
Okay, so the RL problem. So one of the most fundamental quantities in reinforcement learning we're just going to talk about in a bit more detail now, and this is the idea of rewards. So a reward, what is it? Well, it's just a number. It's a scalar feedback signal, this random variable RT. So every time step t, we're going to define this feedback signal, RT, saying basically how well is the agent doing at that time step. And the job of the agent is basically to get as many, to sum up these RTs and get as much reward as possible in total. That's what the agent's goal is. And so, is this really a good way to understand what we mean by goals? Does this cover what we mean by goals in all kinds of different problems? Well, what we follow in reinforcement learning is kind of based on the following premise, which is a hypothesis, if you like, informally, which is that all goals can be described by the maximization of expected cumulative reward. So there's nothing that we mean by goal following which can't be described by some scalar feedback signal and the maximization of that feedback signal over time into the future. So, that's a little bit controversial. So you should think about that. Do you agree with it? What do people think? Is this something you agree with? We're certainly going to be following that and using that as the premise for the remainder of the course. But it's okay if you've got, in the back of your mind, well, really? Can you do this, this, or this? So just have a think about that for a second. Any thoughts? Do people object? Are they happy?
What
I'll take
if the
silence as
reward's
happiness.
just at the end of the game? There's no intermediate reward. How would you wouldn't be able to use reinforcement learning where that was the case, would you?
So intermediate rewards are fine? Or
No intermediate rewards. It's all at the end. So you
Okay.
don't know anything until you get to the end.
That's absolutely fine. So that just means that we're defining the goal then. So if there's no intermediate rewards, is the question, what happens? And then in that case, what we define is that we define an end of episode, and we define a reward at the end of the episode. And now the sum of the rewards is exactly how well you do at the end of that episode, and the goal of the agent is to pick action so as to maximize that expected sum of rewards at the end of the episode.
So what if the goal is, say, to pass some sort of challenge within the shortest amount of time? So it's...
Okay, so the question was, what about if it's a time-based goal, like if the goal is to try and do something in the shortest amount of time? So typically what we do there is we define the reward signal to be -1 per time step. And then again, there's a termination of the episode at the end of when you actually achieve your goal, you stop. And now it's a well-defined objective to maximize your cumulative reward, basically minimizes the time that it takes to reach goal. So let's actually make this concrete again by talking about some different rewards. So let's actually look at the examples we used. So we started by talking about the stunt maneuvers in a helicopter. So we have, in that case, the rewards might take the following form of a positive reward each time we follow the desired trajectory or come within some epsilon radius of where we want to be, and a large negative reward for crashing. Really, crashing should be bad. It should learn to not do that. If we're playing a game like backgammon, there would be 0 intermediate rewards to follow the question, but at the end of the game, we would give a signal saying, if you won the game, that's good. If you lost the game, bad. And then the agent just figures out for itself how to maximize those rewards, and it will learn to take decisions along the way that will maximize at the end of the game how well it does. If you're managing an investment portfolio, I guess one of the good things about finance has a very clear reward signal, which is dollars or pounds, and so in that case, the goal is simply to maximize the total reward. Controlling a power station, there would typically be some positive reward for each unit of power that's produced by this power station. But there might also be negative rewards for exceeding safety thresholds or doing something which is not, maybe there's regulations by the regulator which have to be respected. And if you want to make a robot walk, you might have a positive reward for forward motion. Each unit of distance that you travel might perhaps give a unit of reward. And there might be, again, a large negative reward for falling over. So each of these examples of problems where they're very different problems. They might not feel at first glance like there's a common framework for all of these, but our goal is going to be to build a unifying framework where within machine learning we can address all of these different types of problems within the same formalism and therefore solve them all using the same agents and the same ideas. And so the first step is understanding the reward signal, that we get a reward at every time step. Okay. And in the Atari example, finally, in that case, we just gave a positive or negative reward for each change in score at every step. Like if you got 10 more points in that step, it'd be a plus 10 reward at that time step. Okay. So now, what is this framework? You should be asking yourself, well, these are all really very different problems. How can we even imagine a unifying framework for all of them? And so, we think of this as sequential decision making, and the goal in each case is the same. That's what unifies them together. But the goal is to select actions so as to maximize the total future reward. We basically want to pick a sequence of actions so that we get the best results, the most total reward along our trajectory. And in particular, we need to note that what that means is that we have to plan ahead, we have to think ahead, because actions may have long-term consequences, and the reward that we get might not come now, it might come at some future step, and sometimes that might even mean that you have to kind of give up some good reward now so as to get more reward later. So you can't be greedy when you do reinforcement learning, you have to think ahead. And examples of that would be, like a financial investment where you have to spend some money now, so you're losing money, you spend some money, but then you believe that later you'll get more money back once this matures. Or if you, in the helicopter example, maybe it's running low on fuel, so you might want to stop, lose some reward for following your maneuvers to refuel for a while, but that might prevent a crash in several hours' time and therefore actually lead to longer runs and more reward in the long run. Or if you're playing a game of backgammon or chess or something, you might want to choose a move which doesn't look like it's going to make you immediate gains. You don't take the opponent's queen, but instead you do some strategic thing which helps you much later on, because you think that blocking your opponent now might help you do better later on in the game. Okay, so the formalism we're going to use, we're just going to develop that a little bit in terms of this interaction between agents and environments. So I'm going to use this big brain thing here to represent the agent, So this is the thing which we are controlling. Our goal is to build this brain. We want to build an algorithm which is going to sit inside the brain of something we're going to call the agent, and that thing is going to be responsible for taking actions. Like, it's able to take actions like deciding what the torques are going to be on the motor for controlling the robot, or deciding what investments to make or what moves to play. Those are the actions that our algorithm, our agent, is able to make. And at each step, those actions are taken based on information that it's receiving. So at every step, it basically gets to see something of the world, like it might be a robot with a camera, and it gets to see a snapshot of what's happening at that time in the world. And it gets some reward signal. This is our reward that we've just discussed, saying how well it's doing at that step. And that's it. That's all the agent sees. It gets the observation coming in, reward coming in, it has to make a decision. So that's our goal, is to figure out algorithms that sit in this brain here. On the other side of the fence, we have an environment. So I'm going to represent the environment by this sort of world. This is what's out there on the other side of the agent, the thing it's interacting with. And what's going to happen is there's this loop over time. You can think of this loop where the agent is interacting with the environment, and at every step it's seeing something of the world. It gets some observation where it's seeing a snapshot of the world at this moment. The agent's wandering around seeing stuff. And the environment is generating what that observation will be and what the reward is. So if you imagine this is the Atari environment or something, then there's some actual real Atari game that's generating the next observation, the next screen, and the score. But we're not controlling that part. We have no control over the environment except through this channel here. We get to influence the environment solely by the actions that we take within that environment. So the agent influences the environment by taking actions within it. A robot can move around and influence it where it is within the environment, or where objects are, and so forth. Okay? So an interaction between agent and environment. And this just goes on, and the trial and error loop that we define for reinforcement learning is basically a time series of observations, rewards, and actions, and that time series defines the experience of the agent. And that experience is the data that we use for reinforcement learning. So the machine learning problem of RL is concerned with this source of data, this stream of data coming through, observations, actions, rewards.
We always limit ourselves to just strictly a scalar reward, because, for example, I can imagine interacting with a world and I make a decision that, like, increases my standing with my boss but pisses off my girlfriend, for example, and I might, like...
Good. Okay, so the question was, do we have to limit ourselves to a scalar reward? So I thought people were suspiciously silent, so let's go back to this hypothesis. So the reward hypothesis was that the reward is a single scalar feedback signal, and a scalar feedback signal is sufficient to describe everything we mean by goals. So the question is, well, sometimes there are, maybe different conflicting goals that you might have, and how do you know which of those it is that you care about optimizing at any given time? And so I guess the RL view of that would be to say that ultimately the agent has to pick actions. And to pick actions, you have to be able to weigh up these different goals, because ultimately you have to pick an action. You have to decide whether you're going to meet your girlfriend, or whether you're going to, do the other thing you care about. Go to work.
Stay late.
Stay late at work, or hang out with your girlfriend. And you have to pick amongst those ultimately. And so to pick amongst them, you need to be able to compare them. And in order to be able to compare two things, you have to be able to line them up on an axis, which kind of implies that you have some scalar, there's some scale on which you can compare them, which can be converted into a scalar reward. So there's always a conversion. Ultimately, there must be a conversion into a single thing that you can decide over, and so a scalar reward ultimately must be enough. That's the RL view. Not everyone has to agree with that. Okay. So this stream of experience that comes in, this sequence of observations, actions, rewards, we call it the history. So the history is what the agent has seen so far. So each step it takes its action, sees an observation, sees a reward, all the way up to the current time step t. And the history, ht, is basically the sequence of everything it's seen so far. And that's, in some sense, this is all the observable variables. Like, there might be other things hiding inside the environment, but the agent doesn't know about those. It can't observe those things. And so in some sense, they're irrelevant to the algorithms that we create. The algorithms that we create can only be concerned with what the agent can actually see. Remember, we're trying to build that brain. The algorithm sits in that brain. And so we should only concern ourselves with what the brain is actually exposed to. And so you can think of this as like the sensory motor stream of a robot or an embodied agent. But this also applies more generally. You know, a game-playing agent or a trading agent, it has its own sensory motor stream of, you know, what the inputs are that it's seeing and the decisions that it's able to take. There's some well-defined interface between agent and environment, and we just get to control and see this stream of stuff that's coming into the agent from its environment. And what happens next actually depends on this history. So the agent, you know, our algorithm, we get to build something which is essentially a mapping from this history to an action. So that's our goal, is to build a mapping. An algorithm is a mapping from one of these histories to picking the next action. So what happens next from the agent's point of view depends on the history. And what the environment does is the environment looks at what it's received. It looks at the history of what's happened in terms of the agent, and it also looks at the history, and it uses this history to decide what it's going to do next in terms of what observation it's going to emit at the next time step. So this history literally determines the nature of how things proceed. The history determines what happens next. But it's not very useful. The history isn't very useful because it's typically enormous. You know, we want to have agents that have long lives and can deal with microsecond interactions, and each of these observations may be a video, and we don't want to have to go back to this history every time. And typically what we talk about instead is state. And so state is like a summary of the information that's used to determine what happens next. So in other words, if we can replace the history by some concise summary that captures all the information we need to determine what happens next, then we've got a much better chance to do some real things with our machine learning. And we're going to spend some time talking about state. I think it's a really crucial concept that's widely misunderstood, and I really want to carry this over really carefully. So formally, what is state? So every time step t, we can construct this state, which is a function of the history. So it's just any function of the history. That's the definition of state. So, you know, a valid definition of state would be to only look at the last observation, for example, and just ignore everything that's come before, or to look at the last 4 observations. That's actually what we did in Atari. Pretty simple. Okay. But there's many different definitions of state, and what I want to pick apart now is at least 3 different definitions of state to understand what they really mean and how they relate to each other. So the first definition is what we call the environment state. So the environment state is basically the information that's used within the environment to determine what happens next. So if you think about it, there's some in this world. Imagine this is, you know, the robot interacting with some real environment. That real environment has some sort of set of numbers determining what's going to happen next. Or if this is the Atari emulator, the emulator has some internal state that's going to decide what that emulator does next. Or if this is, you know, a factory, what happens to that factory has some process that's going to decide what happens next. And there's some set of numbers that determines what happens next from the environment's point of view, based on what it's seen so far, its history, and there's some state that summarizes everything it's seen, and which will spit out the very next observation and reward. And so we call that the environment state. This is literally, you know, what, if you kind of informally were to say what state is the environment in, it's the set of numbers that is contained in here, the information that is necessary to determine what happens next from the environment's perspective. So the special thing about the environment is that it's not usually visible to the agent. So, you know, we don't get to look inside our crystal ball, and we don't get to see everything that's happening within the environment. If you've got some robot walking around in the world, it doesn't know the state of all of the atomic configuration of Ayers Rock in Australia. It only gets to see what's in front of it in this video stream that's coming through to it right now. So the environment state, this set of numbers that's determining what happens next, isn't usually visible to the agent. So it's more like a formalism that helps us understand what an environment is than something practical that helps us build our algorithms here. Our algorithms cannot depend on these numbers. Our algorithms don't see these numbers. Our algorithms just see the observation coming in and the reward and the actions coming out. And furthermore, even if we could see this information, sometimes it might not be the right information that we would like to use to make effective decisions here. So again, you know, the configuration of Ayers Rock isn't probably very relevant to the robot that's wandering around this room right now. It needs to be able to look at its own stream and understand what's locally around it to be able to make good decisions. And so actually having its own subjective representation may be a good thing. Yes, question?
If you put a lot of agents together influencing the same environment, do you get any sort of self-organized behavior patterns or anything like
So,
Did you notice anything?
okay, so the question is about multi-agent systems. So I just want to say one thing about multi-agent systems, which is essentially they're beyond the scope of this course, but let me just briefly say that from the perspective of each individual agent, it can consider all of the other agents that it's interacting with to be part of the environment. So from the perspective of one brain here, the fact that there are other brains wandering around in this environment doesn't really change the formalism. It doesn't have to change the formalism. There's just one agent interacting with them. Your question, I think, is whether the emergent behavior shows some patterns between the brains here and the brains there. It can, and there's a lot of work on that, but it's kind of beyond the scope of what I'm going to talk about in this course. Right. So the environment state doesn't tell us anything useful for actually building algorithms. We don't see that. So instead, we talk about the agent state. The agent state now is the set of numbers that actually lives inside our algorithm. So within our algorithm, we're going to have some set of numbers that we use to basically capture exactly what's happened to the agent so far, summarize what's gone on, summarize everything it's seen so far, and use those numbers to basically pick the next action. So whatever information we choose to store and capture here is what we call the agent state. Whatever information is used to pick our next action, that's what we call the agent state. And that's our decision. Our decision is how to process those observations and what to remember and what to throw away. And that, there are many different choices there which we'll talk about. So, and this is the information that's used by our reinforcement learning algorithm. So when we build an RL algorithm, we'll really always be talking about the agent state, that we'll be thinking about, you know, formalisms where we take an agent state and we build something that picks actions from our state. And that's really our goal then, is to really understand how to pick actions given some state that summarized everything we've seen so far. And this state can be any function of history. This is our choice. We can build this function. That's part of the agent. The agent gets to decide what this function is going to be, how it's going to convert the history of all of the actions and observations and rewards it's seen so far into a useful, say, vector of information that's going to be used to characterize its future behavior. Okay, so that was two definitions of state, agent state and environment state. Now here's a more mathematical definition of state, which we call the information state, or sometimes called the Markov state. And the Markov state, or the information state, basically is an information theoretic concept. It tells us when we've built a state representation that contains all useful information from the history. So what we're going to do is we're going to define something. We're going to define a Markov property. So this is the Markov property. It's probably familiar to those of you who've studied anything to do with Markov chains or anything like that. It's the same idea. And the Markov property basically says that the probability of the next state, conditioned on the state you're in, is the same as the probability of the next state if you showed all of the previous states to this system. In other words, you can throw away all of the previous states and just retain your current state, and you would get the same characterization of the future. So let's just try and understand what that really means. So I like to think of it this way, that what this is really saying is that the future, what's going to happen in the future, if you have the Markov property, then the future is independent of the past given the present. In other words, that you only need to store this ST here. If you've got this state representation S and it's Markov, you can throw away the whole rest of the history. You don't need it because that history doesn't give you any more information about what will happen in the future than the state that you have. That's what the Markov property means. It means you can throw away everything that came before, just keep your state, and you're good because you haven't given up anything. That state still characterizes everything about the future, all future observations, actions, rewards. The distribution over those events is the same conditioned on your state as it is conditioned on the whole history. So you can just give up this, work with something much more compact, and everything will be fine. So that's the definition of a Markov state. So we can throw away the history now. And another way to say the same thing is that the state is a sufficient statistic of the future. So this state here fully characterizes the distribution over future actions, observations, and rewards. So once we have this state, we can say everything that there is to say about that distribution. Yeah, question?
I think you said at the beginning, though, that the reward comes at many time steps after the action, the observation, and the action.
Yes.
So, I mean, how does that reconcile with the fact that you're throwing everything away except the previous time step?
That's fine. So all we're saying here is that the way that this environment is going to evolve going into the future, that everything we can say about the future, the distribution of events that might happen to us, conditioned on this state is the same as if we conditioned on the full history. So we still have to figure out how to take the right actions. We still have to figure out what the optimal behavior will be. All this tells us is that if we make decisions based on S, those decisions can still be optimal because we haven't thrown away any information. We haven't talked yet about how to make decisions based on S rather than H. Yeah.
Give your example of a helicopter, for instance, because clearly where it goes next depends on where it was before.
Okay, so the question was, how does this fit in with the helicopter example? So for the helicopter example, a Markov state for the helicopter would be the current position, velocity, angular velocity, angular position of the helicopter would be roughly a Markov state for the helicopter. Once you know all of those things, and maybe you need to know the wind direction and things like that as well, but if you know all of those things, it doesn't matter what the position of the helicopter was 10 minutes ago. That doesn't make any difference to where the helicopter will be at the next moment. All that matters is where it is now, and the wind direction, and that will fully determine what will happen to the helicopter at the next moment. You don't need to remember this detailed history of its previous trajectory, because it's irrelevant. In contrast, let's say you took an imperfect state representation that's non-Markov, like you just had the position but not the velocity. Okay? Now, where the helicopter is does not fully determine where it will come next, because you don't know how fast it's moving. And so you have to look back in time to figure out actually what its velocity is and what its momentum will be, all these kind of things. Okay. So that's the information state or the Markov state.
Can I just ask one question? On this, we're saying that the state, if we know the state, then we know everything there is to know about future states.
Yes.
So that itself is not necessarily very helpful, because the state might be nothing to do with the reward.
Okay, so this history, don't forget that the history includes all rewards. So to say that it's a sufficient statistic of the future means that it's a sufficient statistic of all future rewards. So that, by definition, means that a Markov state contains enough information to characterize all future rewards. Okay, so I want to give two just brief examples before we move on. So one thing to note is that the environment state, if only we had access to the environment state, that would be great, because the environment state is Markov. By definition, the environment state fully characterizes what will happen next in the environment, because that's what the environment is using to pick its next, the next observation it's going to emit is and the reward. So sort of by definition, the environment state is Markov. Also by definition, if we keep the entire history of everything, that is also a Markov state. It's just not a very useful one. But if we retain everything and make our decisions based on the entire history contains as much information as the entire history. It's sort of tautological, so therefore it's Markov. So these are two examples where we can, to show that there's always a Markov state. It's always possible to come up with some Markov state. The only question is, in practice, how do we find a useful representation? Okay, so let's just make this concrete with one example. So this example, we've got this rat, and I want you guys to be the rat. Okay, and I'm going to be the evil experimenter who's going to either give you a piece of cheese, or if you don't do what I like, then I'm going to electrocute you. Okay, so here's a few sequences that you observe. So you're learning by trial and error. So light comes on, you pull a lever, hear a bell, and then zap, I electrocute you. Okay, sorry. Second episode, you hear a bell, see a light come on, you pull a lever again, and you get a delicious piece of cheese. Okay. Third episode, pull a lever, see a light come on, pull a lever again, hear a bell, and now you need to predict for me. Are you going to get electrocuted, or are you going to get a delicious piece of cheese? Okay. So let's have a show of hands. Based on this experience that you've seen so far, if you were this rat, how many people think that you'll be electrocuted? Okay, a lot of people. How many people think that you'll get a delicious piece of cheese? Okay, a few. And can someone say why you thought, so someone from the electrocution, why did you think you'd be electrocuted?
Because of the bell. So from the past experience, when you hear a bell after the lever, you get electrocuted.
Okay.
While in both cases you have seen a light before the lever, so we're not sure about it.
Right, so the comment was that the recent history was the same. So we've seen light, lever, bell here, light, lever, bell here. So from the last three, we would expect there to be electrocution. So another way to say that is that if you're a rat and your agent state, the state that you're using to make your decisions is the last 3 things in the sequence, then you would believe that you're going to be electrocuted. However, that's not the only choice for state. You might, for example, choose the agent state to be counts for the lights, the bells, and the levers. So if that was your agent state, then you might count them up and say, hey, look, in this example, we see the lever's being pressed twice, the light has come on once, and the bell's sounded once. So that's exactly the same as this second episode here. So if that's our representation of state, we would expect that the cheese would appear now. So it should be clear that what we believe will happen next depends on our representation of state. So what about this one? What if the agent state is the complete sequence? What will happen next? If we think that the next thing which happens is the complete sequence we've seen so far, what will happen next? We don't know. And that's another legitimate case. It might be that actually the environment, what happens next does depend on the entire sequence, and you just have to see all 4 things before you know what happens next, in which case we just don't have the data to decide yet. So the state representation really defines what happens next in some way that can be characterized in all kinds of different ways. And in some sense, our job is to build an agent state that's useful, that is effective in doing the best job of predicting what happens next. Okay. So let's finally, on this part, just talk about a couple of special cases. So fully observable environment, this is what we're going to work with for a lot of the remainder of the course. So this is the nice case. So this is the type of environment where we get to see everything. The agent literally gets to see what's going on in the environment state. So it gets to look inside, see the numbers inside the environment, and work with those numbers. So that's the best case. And so another way to say that is that all of these things collapse to the same quantity. So the observation that we see is the same as the agent state, which is the same as the environment state. We get to see the environment state and use it as our agent state. And when we work with this type of representation, we come up with the main formalism for reinforcement learning, which is called a Markov decision process, or MDP for short. And we'll spend the next lecture actually understanding MDPs in more detail because they're a really powerful tool. But I really want people, when we go through the rest of the course, to remember these ideas of state representation, because not everything is fully observable, and it's really crucial that we understand how to deal with these other very realistic problems. And luckily, the MDP formalism, which we'll develop, actually also helps us to deal with those cases too. So what about the other case? The other case is partially observable environments. So this is where the agent indirectly observes the environment. So it doesn't get to see everything about the environment. So for example, a robot with a camera, it might not know exactly where it is unless it has a GPS. Maybe it just gets to see this camera stream. And it has to figure out for itself where it is within the room. It has to localize. Or another example would be a trading agent. This trading agent might only observe the current prices, but it might not know, the trends or where these prices are coming from. It has to just figure out what to do next based on partial information. Or a poker playing agent that only observes the public cards, the cards which are face up on the table, and doesn't know what's hiding in someone else's hand. These are all examples of partial observability. And in all of these cases, the agent state, we have to build a state that's distinct from the environment state, because we don't know the environment state. We don't know what's in the opponent's hand or what's hiding behind the environment that's driving the prices. We don't know all that information. It may as well not exist as far as the brain is concerned that we're trying to create. So this needs a different formalism, and this is known as a partially observable MDP, or a POMDP. And now our job is to build this agent state. We have to build this SAT. So how do we do that? Well, there's lots of ways we could do it. The naive approach is just remember everything. So remember all of the observations, actions, rewards we've seen so far, and say, hey, that whole thing, that whole sequence is going to be our state. Let's work with it. Or we can build beliefs. This is the probabilistic or Bayesian approach. So at every step you build beliefs over where you think. So you think, okay, I don't know what's happening in the environment, but I'm going to keep a probability distribution over where I think I am in the environment. So I'm going to have some probability that I think the environment state is S1, some probability the environment state is Sn, etc. And this whole vector of probabilities defines the state that we're going to use to actually decide what to do. So you actually keep a whole probability of all of those things. So that's not the only choice. Another choice is to do something, you don't need to use probabilities at all. It's not necessary. We can have any numbers we want inside our agent. for example, a recurrent neural network. So that basically means that you take your agent state that you had at the previous time step, and you just take a linear combination of the agent state you had at the last time step with your latest observations, and that gives you a new state. So you just have some linear transformation of your old state to your new state that takes account of the latest observations, have some nonlinearity around the whole thing, and that gives you a new state. So that's the recurrent neural network approach. Okay. Any questions before I think I missed one? Yeah.
Just to clarify, for instance, between these two descriptions in your Atari game, full state would presumably be knowing the rules of the game. So the agent would sort of realize what the rules are.
So the question was, can I clarify what's going on with the Atari example? So let me just jump forward. I have a figure here to help clarify that, which I was going to do later, but maybe it's helpful to do now. So this is what the RL cycle looks like between agent environment in the Atari example. So in the Atari example, we basically have the agent is making its decisions. It gets to take actions, which are to control the joystick. The environment in this case is the actual machine, and it's got some cartridge in it which determines the rules of the game. We don't know what's on this cartridge. We don't get to see it. We don't know how it's picking its next screens that it's going to show us and the next scores. But that cartridge, given the actions that we take on our joystick, will determine both what it shows on the screen and also the score. Those things are fed into the agent, and it gets to take a new action as a result. So the state in this case, the environment state would be the set of numbers. There's 1,024 bits in the emulator. It's a 1,024-bit machine. So there's exactly 1,024 numbers, binary numbers, characterizing what's going on inside this Atari. And those have to be enough to tell it what to do next. And inside the agent, we have some representation, which in our particular algorithm was just a stack of the last 4 things we've seen. And that was the information that we used to decide what to do next. Okay. Right. So let's open up an RL agent and see what's inside. So far, just to clarify, we've talked only about the problem. We haven't even mentioned how to solve the problem. We've just talked about what it is to define this reinforcement learning problem. So what I'd like to do is talk about the main components of an RL agent. What are the main pieces that go inside it? And we're going to use that to build a bit of a taxonomy of how we talk about reinforcement learning. So an RL agent may include one of these 3 things. These are the main objects for reinforcement learning. They're not the only ones, so I don't want you to think this is an exclusive list. But these are the main concepts that we're going to talk about, the main pieces you may have or not have inside your agent. The first one is what we call a policy. So this is how the agent picks its actions. It's its behavior function. It's the way that it goes from its state to a decision about what action to take. The second idea is what we call a value function. This is the thing which basically says, how good is it to be in a particular state? How good is it to take a particular action? How much reward do we expect to get if we take that action in this particular state? That's the idea of the value function, a really central idea to a lot of reinforcement learning, estimating how well we're doing in a particular situation. And the third quantity is what we call a model, which is how the agent thinks the environment works. So not the real environment, but the agent's kind of view of the environment. It's got its own model of how the environment may or may not work. Okay. Now these are not always required for an agent, but these are 3 pieces that may or may not be used. Okay, so let's just go through them one by one. So the policy is essentially a map from state to action. So if we're in some state S, then we could have a deterministic policy. That's one choice. It's like just a function now. This function pi tells us how to get from some state S, summarizing the situation we're in, to some action A. This is the decision the agent takes. And so this policy is really the thing which we care about. We want this thing to, we want to learn this thing from experience, and we want this policy to be such that we get the most possible reward. So that's the game we're playing, is to try and, the brain we're trying to build is the thing that figures out this policy. We can also learn a stochastic policy. So there's no reason our policies have to be deterministic functions. They can also be stochastic, and often this is very useful. It helps us to make random exploratory decisions, for example, to see more of the state space. And so this is just a probability of taking a particular action conditioned on being in some state. So it's a stochastic map now from states to actions. And we'll talk about both of those in this course. Okay, the next central quantity is the value function. So let's really try and unpack this a little bit. So the value function is a prediction of expected future reward. So why do we need this? Well, we need this to say, if you want to choose between state 1 and state 2, or between action 1 and action 2, how do you choose between them? Well, we want to be able to choose on the correct basis, and the basis that we're trying to use here is how much total reward we expect to get in the future. So the expected future total reward is what we mean by a value function. So formally, we typically write it something like this. So this would be a value function, and the value function depends on the way in which you're behaving. So we have to index it by pi here. So if I was to have a robot which is falling over a lot, that robot will get a very different total reward to an agent which is standing up or walking effectively. So the amount of reward that we get depends on the policy. And so the value function for a policy tells us how much total reward we expect to get going into the future. So we're going to look at the expectation over the future of the reward at time t, plus the reward at the next time step, plus the reward at the next time step. And we can also have this discounting going into the future. This is something that says we care more about immediate rewards than later rewards. So we'll understand this in more detail next lecture, but just to give you some intuition, this is a really central idea that we care about basically how much total reward we can get from some state onwards if we're going to follow this particular behavior. If I'm in my helicopter and I know that I'm going to execute some particular trajectory, how much reward will that trajectory get me? That's what we're trying to say here. And if we can compare these things, then we've got the basis to make good decisions, because we know which of those, should we choose the trajectory that's going to get us 73 points of reward in total, or should I choose the trajectory that's going to get me 65 points of reward? Well, it's obvious when you say it like that. So the value function is a really helpful quantity for optimizing behavior. Okay, so I'm just going to do one more video just to make this idea a bit more So this is the value function in Atari. So what we're looking at here on the top right, if we look at the top right, is exactly this quantity V that we were just talking about, saying how much reward the agent thinks it's going to get going into the future. And the one down the bottom is saying how much reward it thinks it's going to get for each different action. So just back up a little bit. And what you'll notice is that there's this sort of oscillating behavior where each time the bat is getting, each time it hits the ball, it was going to get more reward. Let me just back up a second. We can look at that. Here. So each time the ball is getting closer to hitting something, it knows it's just about to get this reward. There's no uncertainty left. And so it gets this big spikes in the reward according to this. And each time the ball's coming back down, the predicted future reward is going down. And so you get this sort of oscillating behavior. And it's only when the agent's actually close that it matters which way it goes. It has to make a decision when the ball's coming down of whether to go right or left. And until it gets right there, it doesn't really matter which one it chooses. Now for Space Invaders, what we see here, let me just back up again, is that what we see is that there's basically, we'll see a big spike, which is when the mothership starts coming along the top, it realizes that mothership might mean a big spike in possible reward it's about to get. Like if it actually shoots that mothership, it should expect to get a very large positive reward. And so when that appears in its state, when it starts to see this thing, its prediction of future reward should go up. And so that's what we see, is that now this mothership comes up, the value function starts to climb, it misses the opportunity to get it, and the value function goes back down again. Now we see another example. The value function is kind of flat, it's getting all of these things as it's shooting. Here comes the mothership. This time it shoots it, and the value function still goes back down, because we're always just talking about the future reward. The value function is how much reward we expect to get in the future. So the fact that we've just got that reward, so now we've received that reward, but we still predict that we're going to get less reward from now on, because the mothership's already come, we've shot it, it's probably not going to come again for a while. Okay, so we've got like this agent's internal measure of how much reward, how much score it's going to get going into the future from here. And this thing is like its oscilloscope of how well it's doing at any given moment in time. So it can be used to make decisions.
So
Yeah.
So this reward is predicted let's say 1 second, right? It's not predicting the end of the game, or just
Yeah, the reward has a time scale to it, and the time scale. If we just go back to the time scale. So the question was: is there a time scale to how far ahead we look in? Is there a horizon to how far ahead we look into the future for these scores? And the answer is that the horizon is given by this discount factor. So at every step we discount the reward a little bit more and a little bit more and a little bit more going into the future until essentially we don't care about things very far into the future. So for that particular example, it was about 0.99, the discounting, which means that we're essentially looking, say 100 steps into the future. Yeah.
Is there some sort of a risk-reward trade-off between the value functions? So for example, you care about value functions which have a lower expectation but are more stable in terms of actions you do.
Okay, so the question is there some kind of risk trade-off that you can make where you can, for example, can you balance variance of these reward predictions? The answer is that ultimately what we care about, we've defined a formalism in which what we care about is just the amount of reward we get, and if you care about just expected reward, then risk is already factored in, that you will figure out the behavior which correctly balances risk automatically if you optimize for this. However, there are people who specifically try to do, for example, trading, who take account of risk, and there's risk-sensitive markup decision processes which do try to explicitly account for this. So if you really want to bring in risk, you can, but I think the right way to think of this is that risk is already accounted for, that it will automatically, the behavior that maximizes value is the one that correctly trades off the agent's risks so as to get the maximum amount of reward going into the future. And that just automatically emerges from the formalism. Okay. So remember we talked about these different quantities. So we've had the policy and the value function. So now let's talk about models. So a model is basically, it's not the environment itself, but sometimes it's useful to imagine what the environment might do, to try and learn the behavior of the environment, and then use that model of the environment to help make a plan and to help figure out what to do next. So specifically, the way we normally do this is to have two parts to our model, transition model and a reward model, where the transition model is basically predicting what the next state will be, predicting the dynamics of the environment. So if this was the helicopter, this is the thing that says that if you're in this if the helicopter's facing this way in this position with this angle, and the wind is coming in this direction, then it's likely to move to this position and this angle, and so forth. That's the dynamics of the environment. And we can try and model those dynamics. We can try and learn what will happen to that helicopter at the next step and figure that out. And we can also learn to predict how much reward we'll get. So we can learn that if the helicopter's in this situation, that it's not crashing and that we'll get one reward for staying alive or whatever it is. And so formally we break this up into a state transition model that just tells us the probability of being in the next state given the previous state in action, and a reward model that tells us the expected reward given the current state in action. Okay, so it's optional to do this, and actually a lot of the course will focus on model-free methods that don't use a model at all. So this isn't a requirement. It's not necessary to explicitly build a model of the environment, but it is something you can do. So let's try and make these concrete in a very simple example, which is a maze. So this maze example is like a canonical RL problem. These little grid worlds, we use them for sort of didactic purposes. And so the idea is we're going to start here and try and get to this goal here, and there's going to be a -1 per time step reward, just like the question earlier. The goal here is essentially to solve this maze as quickly as possible, and that's reflected by this -1 per time step, and the problem will finish when the agent reaches the goal. So solving this, the optimal solution will be just to whiz around it as quickly as possible. And the actions are just like four connected, like it can go north, east, south, west, and the state is basically the agent's location in this grid. Okay? So an example of a policy would be represented like this, that these arrows are an example policy that sort of represents what the agent would choose to do if it was in any one of these states. So this is an example of a deterministic policy function that says, if I'm in this state, go left. If I'm in this state, go up. If I'm in this state, go right. It's a mapping from states to actions. Once you have this mapping, you can just kind of read it out and behave. Like the agent can just read out its behavior and just move all the way to the goal, and we'll get there. So that's what we mean by a policy. We mean like these arrows here. The value function, remember we're going through these three key concepts. So the value function looks something like this. This is the value function for each of these states, where we know that if we're just about to reach the goal, we're only one step away from the goal here, So this must have a value of -1. Here we're 2 steps away from the goal, so this has a value of -2. If we go all the way back to here, we have a value of -16. We can have worse values. You know, if we're stuck over here and we've gone the wrong way, we might have a value of -24. Now we have these values. It's very easy to build an optimal policy because, for example, when we get here, we can just look up what's the value of going north compared to the value of going south, and it's very clear that the value of going north is greater than the value of going south, and so this is useful gives us a basis for optimal behavior. And finally, a model. So let's say the agent has seen one trajectory through this maze, kind of moved around like this, and then it reached the goal, and now it tries to build a model of how this environment works. So you can think of this as it's trying to kind of build its own map of the environment. It's trying to figure out what will happen in the environment. And the model in this case would look something like this, and these -1s represent the fact that it's seen that you get -1 per step, and this map represents what it's understood of the dynamics of the environment so far. It understands that as you move around, these are the transitions where you can move from state to state. It's not reality, it's just the agent's model of reality. Okay. So when we categorize RL agents, we can basically build a taxonomy now, where we can taxonomize all of reinforcement learning according to these 3 quantities. And the way that I taxonomize RL is basically by which of these key components our agent contains. And so we say that when we build a reinforcement learning agent, we say that it's a value-based algorithm if it contains a value function. And if it just contains a value function, the policy is kind of implicit. It just has to read out, look at the value function and pick the best action. Just like when we were here, we didn't need an explicit representation of policy because we could just look at our value function and say, hey, the value function here is higher than the value function here, so always just pick actions greedily with respect to your value function. And so that basically gives us a way to behave and means that a value-based algorithm can look like this, just a value function and no policy, or an implicit policy.
I'm just curious, why in the previous slide we mark all the points with -1?
So the question was, why were the -1s on the previous slide from? So the -1s were the agent's model of how much immediate reward it gets at every step. So it's basically saying it learns, so the setup of this problem was -1 per time step, no matter what happens. And so now the agent's map says that each step it takes, no matter where it moves, it's going to get -1. So this isn't the value, this isn't a long-term prediction of reward, this is a one-step prediction of reward, saying every single step it's going to, you can go from here to here and get -1, here to here you can get -1.
Okay, but we didn't define the direction, right? If we would go from this second to...
Yeah, sorry, it's just in this down here. So the numbers here represent the immediate reward from each state, and it's the same number for all A, just as an easy way to define this. In general, you would want to have a different number for each action. Sometimes there are different formalisms for reward, and sometimes you can have action-dependent reward, sometimes action-independent. It's a good question, but kind of detail. Okay, so to categorize the agents, they can be value-based, or they can be policy-based. So to build a policy-based agent means that now, instead of representing inside this agent the value function, how well it's going to do from each of these states, instead we explicitly represent the policy. And we work with the policy. So those arrows that we had here, so a policy-based agent would maintain some kind of data structure equivalent to these arrows, and it would work directly in that space. It would basically look at how well it does and adjust these arrows so as to get the most possible reward, without ever explicitly storing the value function. So that's what a policy-based agent means. A policy-based agent is one that stores the policy. A value-based agent is one that stores the value function. And we can also have what's called an actor critic, which basically combines them both together and tries to get the best of both worlds. So an actor critic, which we'll see later in the course, is an agent that stores both the policy and directly represents these arrows, and also stores how much reward it's getting from each state. Yeah?
Well, what do you do in the way of exploration? Like, say you...
I'm going to come back to it. The question was, what about exploration? I've got a section on that coming. Okay, so to finish the taxonomy, now we can either have a model or not have a model. So first of all, one of the major distinctions in reinforcement learning is between model-free and model-based reinforcement learning, perhaps the fundamental distinction in RL. So model-free means that we do not try to explicitly understand the environment. We don't try to build the dynamics of how the helicopter moves. Instead, we go directly to the policy or the value function. So we just see experience and figure out a policy of how to behave so as to get the most reward, without going through this indirect step of figuring out how the environment works. So that's model-free reinforcement learning. And a lot of the course will be about understanding how that can be possible. You know, how do you even do this without building a representation of the environment first? Alternatively, we can do model-based reinforcement learning, where we first of all, our first step is to build up a model of how the environment works. We first build our dynamics model of the helicopter, and then we plan with it. We do look ahead. We say, you know, what would happen if we looked ahead with this model and figured out the optimal way to behave? So we have something like this Venn diagram now, where we can either have a value function or not, we can have a policy or not, we can have a model or not. Now, ultimately, you have to behave. The agent has to select actions, and to select actions, really it needs to have a policy to pick it, or a value function that implicitly defines a policy. So the majority of algorithms look like that. Okay, so this is our taxonomy of RL agents and how to understand if you pick up a random paper from reinforcement learning, it will fit in somewhere in this diagram. Okay. So briefly, for the last 5 or 10 minutes, I just want to talk about some problems within reinforcement learning. So we've talked about the reinforcement learning problem overall, but there are some key sub-problems that we're not going to talk about how to solve these, but just to name them and make you aware of their existence and to start thinking about them is my goal at this stage. Okay. So let's start with learning and planning. I think this is maybe the most important conceptual distinction to understand. There's actually two different problems in sequential decision making. So if we go back to this science of what does it mean to make optimal decisions, there's two very different problems we might care about. First of all, there's what we call the reinforcement learning problem, where the environment is unknown. Like the agent isn't told how the environment works. You literally just drop your robot into the factory floor and tell it to get the most reward. Or you turn on your power station and you tell it to go and figure out how much reward it gets. You don't tell it, how the wind blows or how the factory operates. It just figures stuff out for itself. And the way it does that is by interacting with the environment, and through interactions with the environment, figuring out a better policy that's going to maximize reward and get the most possible future reward. So this is the reinforcement learning problem. Doesn't know about the environment, interacts with the environment, essentially through trial and error learning, figures out the best way to behave within that environment and maximize its reward. Okay. There's a second problem set up, which we call planning. Planning is different. We tell it the environment. In the planning problem, we say, this is exactly the environment that you're working within. We tell it all the rules of the game, if you like. We tell it the details of the dynamics of the wind for the helicopter and how helicopters move. We tell it. We give it the differential equations describing wind and so forth. So the model of the environment is fully known. And instead of interacting with an environment, the agent performs internal computations with its model now. It's given this perfect model. It's given computation time. It interacts with its model. Doesn't actually have to do anything in the real world. It just kind of thinks for a while, figures out what to do next. Maybe it's doing look-ahead planning. And as a result of those interactions, it improves its policy and comes up with a way to behave. But they're very different setups. In RL, the environment's unknown. In planning, the environment is known. Now, of course, one way to do reinforcement learning is to first learn how the environment works and then do planning. So they're linked. These two things are intimately linked together, but they're separate problem setups. So let's try and make this concrete again. So let's talk about the Atari problem again. So this, I already went through this slide earlier. But this was the reinforcement learning problem, right? We start, no one told us how this emulator works. We just put our machine in front of this thing, it's trying to figure it out through trial and error. We don't know the rules of the game, we just see the scores on the screen and get to control the joystick. That's the RL problem. What about the planning problem? What would that look like? So what if someone actually told us how the emulator works? What if we actually had access to a perfect emulator of these Atari games, and we were able to do look-ahead planning with that emulator? We could query the emulator. You could think of this as our perfect model now. And we could say, if I was in this state here, in this game Sequest, and I move the joystick right, where will I end up next? Or if I'm in this situation here and I move the joystick left, where will I end up next? And this perfect model will tell us what happens, and that gives us the ability to do things like look-ahead search or tree search or planning. There's all these different planning methods where we can kind of think ahead, and we can say, well, you know, if I went right and then went right again, then I'd get some oxygen, and then I'd shoot these different fish, and I'd end up with a reward of 100, without ever actually interacting with the real environment. So you can kind of build this whole search tree, figure things out, and that's the planning process. But it's a different problem setup. Right? We're told in advance the rules of the game. The environment's known. Yeah, question?
If there's more than only two actuators, like say multi-dimensional actuators, then this really quickly explodes into multiple possibilities of that.
Right, okay. So the question is, what happens to the branching factor of this search space? So at the moment we're just talking about problem definitions. We'll have much more on how to plan effectively and efficiently and deal with large branching factors in later classes. So in practice we can do this. So I just want to cover, just before I take more questions, someone asked about exploration. So this is another problem within reinforcement learning. How do we balance exploration and exploitation? It's another key part of the identity of what it means to do reinforcement learning. So reinforcement learning we can think of as type of trial and error learning. You know, we don't know what the environment looks like. We have to figure it out through trial and error. We have to go find out which parts of the space are good and which parts of the space are bad. But the problem is that while we're doing that, we might actually be losing reward along the way. And so the goal is we want to actually figure out a good policy. We want to figure out the best part of this space. We want to figure out where the gold is in, you know, imagine you've got some pirate hunting for treasure. It wants to find the policy that has the most gold, but along the way, it wants to make sure that it's not giving up opportunities. Until it's found where the treasure chest is, it shouldn't be giving up the opportunities to exploit the things it has discovered. So the one way to say this is it basically gets to interact with experience. It's trying to find the best possible policy without losing too much reward along the way by exploring. So it has to balance exploration and exploitation. In other words, exploration means choosing to give up some reward that you know about in order to find out more about the environment. So, you know, maybe you think, given everything you've seen so far, you think that by going left you'll get the most reward, but you know that you haven't really explored right very much. And so maybe it's better to go right for a while, discover that there's a big treasure chest there, and so that in the future you might end up actually getting a lot more reward in the long run. So we've got this balance between exploration and exploitation. Exploration, find out more about the environment. Exploitation means exploit the information you've already found to maximize your reward. It's the exploration-exploitation trade-off. It comes up, you know, it's universal to reinforcement learning and kind of special to reinforcement learning. It doesn't come up elsewhere in machine learning. So let's just have some examples. So, you know, you all go to restaurants occasionally. So what happens if you're trying to pick the best restaurant? So what does it mean there? So exploitation means you kind of go to your favorite restaurant. Exploration would be trying a new restaurant. Now, how do you balance these? Like if you never explore and keep going to your favorite restaurant, you kind of get stuck on something suboptimal. But if you explore all the time, you end up, you know, maybe eating food that you don't like because you're exploring a lot, and maybe you should have gone to your favorite restaurant a little bit more often. So you have to balance these things out so that you end up finding the best restaurant and eating delicious food along the way. The classic example of this, it's one of the big success stories of machine learning, is advertising online. So this is a big use case for a lot of this machinery, where you're trying to basically decide what advert to show on some banner on some website. So this would be like, you know, Google AdSense or something like this. And there's exploitation then would be to show the most successful advert, the one which people are clicking on the most. But sometimes you also need to explore and show some different adverts that haven't been displayed before to see if people will click on them. And maybe those adverts will turn out to be better, make more income. Or oil drilling, you might want to drill at the best known location, so you know that there's likely to be oil over here, so maybe you just keep drilling and drilling and drilling. But sometimes it might be a good idea to try some new location, drill down a bit, see if there's oil there. Or in game playing, you know, you might play the move you believe is best right now, or you might just try a completely different strategy, something quite experimental, see how your opponent responds. Maybe over the course of many games that will end up being more effective. Okay. So just to finish, okay. So final problem I'll just cover briefly, which is prediction and control. So this is another distinction within reinforcement learning between prediction, which basically means how well will I do if I follow my current policy. So someone tells me the policy, I'm given the policy, if I walk straight forward, how much reward will I get? Now that's a different problem to someone saying, what's the optimal policy? Which direction should you walk to get the most reward? And typically what happens in reinforcement learning is we need to solve the prediction problem in order to solve the control problem. We need to be able to evaluate all of our policies to figure out the best one. And so if we go back to our grid world example, you can have a grid world like this. This again is something where you've got an agent that's moving around this grid world. It's basically gets -1 per time step, but if it goes to A, it gets a +10 reward and teleports to A prime. If it goes to B, it gets a +5 reward and teleports to B prime. We can ask, what's the value function for the uniform random policy? Like if we just move around this grid randomly, how much reward will we get? That's a prediction problem. We're just asking for this fixed policy of behaving randomly, how much reward will we get? This is the answer. You get, at best, if you're in this top state here, you get 8.8 units of reward in total going into the future, roughly. And we'll see how to solve these things in subsequent lectures. If we were doing control, we ask the question, what's the optimal behavior in this grid world? If I'm anywhere on this grid and I behave optimally, now what's the value function? And the value function is very different. So now if we look again at that best state, before we were getting 8.8, now if we behave optimally in this grid world, we get a very different answer. The optimal value, according to the best possible behavior, gives us like more than 24 units of reward, because we're going to follow this optimal strategy and loop round and round these links and get more and more reward. So now it means that if we're in state A, we can expect to get more reward in the future. So the optimization problem, the control problem, is very different to the prediction problem. Okay, so I just want to finish with the course outline, and so people understand what's coming next. So the course is roughly divided into 2 halves. I'm afraid because of last week it won't align with reading week, but we'll figure that out as it goes. But the first part is roughly covering the basics, covering really fundamental understanding of reinforcement learning. So introducing the problem we've just done, understanding Markov decision processes, how to plan, so solving the planning problem using dynamic programming, which is the elementary building blocks that underlie all of this, and then understanding model-free methods for both prediction and then control. In the second part of the course, we'll look at how to scale up, how to really apply, at the end of this part, you won't really be able to go off and solve interesting problems. You shouldn't have that expectation. But all of the ideas which we'll learn here do scale up, and in the second part of the course, we'll understand how they scale up and apply to more interesting problems by using value function approximation, policy gradient methods, integrating learning and planning using more sophisticated approaches, solving the exploration-exploitation problem. And so that's where things will become interesting. And then finally, in the last lecture, which is the one which we'll have to find a good time for that, I'll just give a case study, which is some of the success stories of reinforcement learning in games. And we'll see that RL has been used to achieve not just world champion performance in backgammon, but actually across all of the different classic games,